Hello and welcome. Introduction. In my last video, I showed you how to control an LED on the TM4C123G LaunchPad board using the ADC module of the TM4C123G GH6PM microcontroller. Now, in that video, I used assembly language to control the LED. And now, in this video, I will demonstrate the same process, but using the C language. Hardware setup. Right, the hardware setup is the same as the one I used in my last video, but I will repeat it here for clarity. Now this here is the TM4C123G LaunchPad board, and I'm going to put up the schematic and also expand this part of the board. So we have it here. So here we have a 220 ohm resistor. One end is connected, which is this red connection here. That's connected to the 3.3 volts pin. And the other end of the 220 ohm resistor is connected to the 1K potentiometer. All right, and the middle pin or middle terminal of the potentiometer is connected to PE3 of the LaunchPad board. And the other end of the potentiometer, following this black connection, that's connected to the ground pin of the TM4C123G LaunchPad board. Now the potentiometer allows adjustment of the input voltage, which is fed to the ADC pin of the microcontroller. The program. Complete listing. Okay, so here is the complete listing of the C program. I will go into the details of this program in a few moments, but for now, I'm just going to show you the entire program first. So here, right off here is the header file, and here I declare the functions that I'll be using in the program. And here is the main C function here. Here I declare a variable called ADC result, and here I initiate the 4 functions, and then here is the main portion of the main function. Basically, this line here starts the ADC conversion. Here we send this into a loop to wait till the ADC conversion is done. And basically the main aim here is if the conversion is done and if it's above a certain value here, 2048 in this case, it will turn on the LED. If not, it will turn it off. And here is the beginning of the definition of the functions. So this is the enable clocks function. And here is the initialize port E function. And that is followed by the initialize port F function. And then the last function, which is initialize the ADC0. All right. So this is the complete listing of the program, and we'll get into the details soon. The program explanation. Okay, so let's start off with the this include TM4C123G6PM.h. So this is the header file. Now this header file defines the register macros and the memory map addresses for the TM4C123GH6PM microcontroller and enabling the low-level hardware access. All right. Then these are 4 declaration of functions. First one here is the enable clocks function we declare, and then we declare initialize port E function, followed by initialize port F function, and then followed by initialize ADC 0 function. Then next comes here the beginning of the main function. So here we declare a variable called ADC result, and this is a unsigned integer or unsigned int variable, and we set it or initialize it to 0, and followed by calling or invoking 4 functions which was declared earlier. So here we invoke or we call the functions. So here we call the enable clocks function. We then call the initialize port E function. Then we call the initialize port F function, and then we call the initialize ADC 0 function. So this portion of the program, the one in the red box, is an infinite loop because of this while bracket 1. All right, so it's enclosed in this curly brackets. So these statements here or these tasks here are repeated in this while infinite loop. Okay, so let's take a look at this first statement here. This first statement here basically starts the ADC conversion for the sample sequencer 3 or SS3. Now, ADC 0 and PSSI, these are symbolic names, and the ADC 0 symbolic name refers to the ADC 0 module, and the PSSI refers to the processor samples sequencer initiate register. Now note that the symbolic name ADC 0 points to a base address of the actual ADC 0. Now I'll show you this base address in a few moments. And the arrow operator, the one highlighted here, this is used to access a member of the ADC0 underscore type structure. Now, if all this sounds confusing, I'll show you what I mean by ADC0 underscore type structure in a few moments. And PSSI is a member of that ADC0 underscore type structure. Again, not to worry, I'll show you in a few moments what that means. So before I go any further, let's take a look at the ADC0 underscore type structure. Okay, so I'm in the Kyle Microvision IDE, I've uploaded the code here, put up the code here, and I would like to highlight this header file, which is the TM4C123G6pm.h. Now, you can access this file under the source group file or under the device folder here or here. So if you double click on this, then you will see this file will pop up. So how do you recognize it? You recognize it with the name of the file. And this is the TM4C123GH6pm.h file. Now, I just want to scroll down to, just a minute, getting there. Yeah, so we have the GPIO-A, and this is the register map for GPIO-A peripheral, right? So this is the struct or the structure for GPIO-A, and the name of this structure is GPIO-A underscore type. So this is the name of the structure. And if you notice, the members of this structure is data, dir, is, which is the interrupt sense. Data is the data register. dir is the direction register. Then we have the other one I want to highlight is den. This is the digital enable. Then the next one is the AFSEL. That is the alternate function select register. Then we also have the AMSEL. That is the analog mode select. Now, the reason why I'm highlighting all this is that I'll be referring to these we call structure type and also the members of the structure, right? Which we already seen an example earlier. Let me just go down to find the ADC structure. That's way down here. Just be patient with me. Right, almost there. Yeah, right, here we are. The ADC0. So this is the register map for the ADC0 peripheral. This is the structure, and the name of this structure is ADC0 underscore type. Now, the members of this structure are, which we said earlier, RIS. Then we have the, PSSI, the Processor Sample Sequence Initiate Register. This is a member of that structure, ADC0 underscore type structure. Then we have, we'll be using this later on. So it's the SSFIFO3. This is the ADC sample sequence result, FIFO3. All right, and then I just want to also highlight, which is way down here. I think it's 1.3. Just a minute, just be patient with me. Right, so we have the system control block here. So this is the register map for the SYSCTL peripheral of the system control block. This is the structure, and the name of this structure, which is quite a long structure, struct. This is the SYSCTL underscore type. And the members I would like to highlight is this one here, RCGC GPIO. That is the general purpose input-output run mode clock gating control. All right, run mode clock gating control. And the next one is this one, RCGC ADC. All right, so this is the analog to digital converter run mode clock gating control. Now we will need we need this too to configure or set up the clocks for the ADC and the GPIO. We'll come across that in a few moments. All right. Now, before I finish this, let me just go down to 1579 line. All right. So this is the ADC0 base, and it has this address 4003800 hexa. And we have the SYS, this is 1596. This is what here, SYSCTL underscore base. And then the GPIO one, which is back up here, should have the GPIOA underscore base, and this as an address here. All right. Okay, so these are the base addresses of these registers. So let's now go back to our slides. Okay, so we are back here. So let's take a look at this operator. This is a bitwise OR with assignment. All right, so the value 0x08, this is 08 hexa. If you translate that to binary, that would be 0 0 0 0 1 0 0 0. Basically, this will set bit 3 here, will set bit 3 highlighted here, and triggers the sample sequencer 3 SS3 to start a new conversion. Now, ADC conversions are not continuous by default. All right, so each conversion must be explicitly triggered, and the sample sequencer 3 SS3 is the selected sequencer for conversion in this program. Now, the statement while brackets ADC0 arrow operator RIS and hex 08 is a loop that checks the raw interrupt status register, the RIS register. Now, that is because this is to check or determine if the ADC conversion is complete. Now, the ADC result equals ADC0 arrow SSFIF03. This statement here reads the ADC conversion result from the SS3 or sample sequencer 3 FIFO register of the ADC module and assigns that to the variable ADC result. Now, and then we come to this statement here. Now, this statement here will clear the interrupt status flag for the sample sequencer 3 in the ADC module. Now, by writing this hex value or assigning this hex value, this set bit 3 of the interrupt status and clear register, the ISC register. And the program indicates that it has completed the ADC conversion and is ready for the next conversion. Now, if the ADC result is greater or equal to 2048, then it will turn on the red LED. Now, if the ADC result is less than 2048, it will turn off the red LED. Now, let's take a look at this statement here. Now, this statement here, the GPIOF is a pointer to the GPIO underscore type structure as seen earlier. All right. Now, data here is a register within or member within the GPIO underscore type structure. And the arrow operator here is used to access the member. The member here is data in the GPIO underscore type structure as seen earlier. And this here basically assigns this value to the data register of the GPIOF. And same here, they will assign this hex value to the GPIOF data register. That will turn the LED off. This one here will turn the LED on. Okay, let me explain why I chose the value 2048. Now, the value 2048 represents half of the ADC's range for a 12-bit resolution ADC. Now, it corresponds, this value corresponds to 0.5 multiply the Vref or the V reference, where Vref is the reference voltage. Now, Vref in our case is 3.3 volts. That's from the TM4C123G LaunchPad Board. Now, using that, therefore, if you multiply 0.5, you multiply it with 3.3 volts, we will get 1.65 volts. Now, keep in mind this figure, 1.65 volts, which is equivalent to the 2048 value that we have chosen in our program. Okay, so this is the enable clocks function, and it is responsible for enabling the system clocks for the peripherals used in the program. All right, so let's take a look at this first C statement here. All right, now this here represents the run mode clock gating control register for the GPIO modules. Now this register, every bit in this register corresponds to a particular GPIO port. So if we look at this hex value here, 30 hexa, translate that into binary, that is 00110000. Now this is bit 4, that is corresponds to port E, and bit 5 here, this bit here, that corresponds to corresponds to port F. And then this is the bitwise OR assignment operator. All right, so it performs a bitwise OR operation, OR operation, between the current value of this register and this hex value, which is binary. In binary is this. All right, and then it assigns the result back to this register. Now, this whole statement here basically is to ensure that bit 4 and bit 5 are set to 1. That is because we want to activate or enable the clock for port E and port F. Right, next we come to this statement here. All right, so this is the run mode clock gating control register for the ADC modules. Again, as with the this register, each bit in this register corresponds to an ADC module. Now, there's only two modules. That is ADC 0 and ADC 1. So if you look at this, okay, before we go into this, this is the bitwise OR operation, and this is the value that it is supposed to perform a bitwise OR operation with the current value of this register. Right, coming back to this, 0, 1 hexa, translate that to binary is this. So it's 0, 0, 0, 0, 0, 0, 0, 1. Now the 1 here corresponds to ADC 0. Remember, each of this bit here corresponds to an ADC module. All right. Now, setting this bit here activates the clock for ADC 0 module. Okay, so this is the initialize port E function. And the purpose of this function is to configure port E bit 3, that is PE3, on the TM4C123G 6PM microcontroller to be used as an analog input for the analog to digital converter, ADC. Now, remember, by default, the GPIO pins are configured for digital functionality. That means input-output. So this function makes sure or ensures the pin is correctly set up for analog operation. Okay, so let's take a look at the first statement of the function. So we have this. Now this is the alternate function select register. All right, so this AFSEL is a member of this structure, as we shown earlier. Now, each bit in this register corresponds to a pin, right? Each bit in this register corresponds to a pin on port E. Now, setting a bit in the port enables, that means set it to a 1, setting a pin to a 1 enables the alternate function mode for that corresponding pin. So if we look at this hex value here, 0, 8 hexa, if we were to translate it to binary, which is this, so it's 0, 0, 0, 0, representing the 0 here. And then we have 1, 0, 0, 0, representing the 8 here. So this is the binary. But take note that this is bit 3. Now that corresponds to port E bit 3. Alright, so setting this bit using the bitwise OR operator, this is a bitwise operator, using this operator, we ensure that the port E bit 3 uses its alternate function. Now we come to this statement here, and this here is the digital enable register for port E. Now each bit in this register enables or disables the digital function for a corresponding pin. Now if we look at this hex value here, we notice this symbol here. Now this is a bitwise NOT operator. So if we take this value, now this value 08 hexa, that is this 0000 1000. So this is 8 and this is 0, and this is the binary of 08 hexa. Now, so when we carry out a bitwise NOT operation, we perform a bitwise NOT operation on this, the result is, so all zeros will become ones and the 1 becomes a 0. So that's the effect of this. So this is a bitwise NOT operator. Now this whole statement here, this whole operation here, clears bit 3, that is port E bit 3. It clears it, that means set it to a 0. Now this will result in disabling the digital functionality. Next, we come to this statement here. Now this here is the analog mode select register for port E. Now each bit in this register enables or disables the analog function for a corresponding pin. So we take this value 08 hexa. If we to convert it to binary, we get this. So this is 8 1000 binary in hexa is 8, and this is 0 in hexa is 0. Now if we have this and we use the bitwise OR operator, basically we are setting bit 3, which is this bit here, PE3, that will enable the analog mode. Okay, so this is the initialize port F function. All right, and the purpose of this initialize port F function is to configure port F pin 1, that is PF1 of the microcontroller, to function as a digital output. Now in this program, port F is used to control an LED. Okay, so let's take a look at this first statement here. So this here is the direction register. Now this register determines whether each GPIO pin functions as an input or an output. Now each bit in this register corresponds to a pin in port F. So if you set the pin to a 1, then it sets the corresponding pin as an output. If you use a 0, it sets the corresponding pin as an input. So if we look at this hex value 0, 2, now in binary, it will be this 0, 0, 0, 0, which is this leading 0 here. And then the 2 in hexa, that is in binary, it would be 0, 0, 1, 0. Now using the bitwise OR operator, which is this one here, right? Port F bit 1 is set to a 1, which is this red color highlighted here. This is bit 1. This is set to a 1. So this bit here, this pin here, corresponding pin, would be in output mode. Then the next statement here looks very similar to this one, but this one is the digital enable register. Now this determines whether a pin operates in digital mode or remains disabled. All right, so each pin, again, in this port F corresponds to a pin in port F. So each bit, it corresponds to a pin in port F. Now, if we set bit 1 to a 1, this enables the digital functionality. So if we look at 0, 2 hexa again, in binary, that would be this. This is bit 1. All right, so using the bitwise OR operator, port F bit 1, port F bit 1 is set to a 1. So this basically ensures port F bit 1 or PF1 function as a digital pin. Right, so this is the initialize ADC0 function. All right, the purpose is to configure ADC0, the analog to digital converter 0, on the microcontroller for single channel processor triggered analog conversion using sample sequencer 3, that is SS3. All right, so let's take a look at this statement here. Now, this is ADC0 arrow operator ACTSS. So this is the active sample sequencer register, and it controls which ADC sample sequencer. There are 4 sample sequencer: SS0, SS1, SS2, and SS3. So this controls which ADC sample sequencer are enabled. So bit 3 in the from this 08 hexa, which is translated to this in binary, and bit 3, which is this one highlighted here, that corresponds to SS3, sample sequencer 3. And the bit, this is the bitwise AND, A-N-D, and bitwise AND assignment of operator, and it performs a bitwise AND between the current value in this register and the result of the bitwise NOT of this value. All right, so here, this one here means the bitwise NOT of 08. That then becomes 0 becomes 1, 1 becomes a 0, and 0 becomes a 1. So this is the complement or bitwise NOT of this. All right, so the current value of this register performs a bitwise AND assignment operator with this complement of this. And the result is then stored back into this register. Basically, this whole statement here effectively clears bit 3. All right, so it disables sample sequencer 3. Okay, so let's look at this statement here. All right, now this here is the event multiplexer select register. Now, the purpose of this register is to determine the trigger source for each sample sequencer. So, but before I go any further, let's look at this hex value here. And this is F000 hexa. Now, the binary version of this is here. All right, the F is represented by these 4 bits here. And these are bits 12 to 15. So they're set to 1, 1, 1, 1. That's F. It's 4 ones in binary. That equivalent in hex is F. And the rest are zeros. All right. Now, the bitwise NOT NOT of this value is this. That means all ones we invert it to zeros, and all zeros we turn them into 1. So this is the result of the bitwise NOT operation. So we get this, and the bitwise AND assignment operator together with this sets these bits, that's bit 12 to 15 to 0. By doing that, by setting these bits to 0, we actually set SS3, the sample sequencer 3, to processor triggered mode. All right, so that's the purpose of this statement. Then we come to this statement here, where this is the sample sequencer multiplexer 3 register. Now, this register determines the input channel for SS3, that is sample sequencer 3. By assigning the 0, that means we're writing a 0 to this register, we select the AIN0, all right, that is port E bit 3. All right, by writing a 0 to this, we are selecting PE3 as the input. All right, let's look at this statement here. All right, so this one is the sample sequence control register 3. Now, before we go any further, let's look at 06. This is in hexa. The binary version of this is this. All right, which is 00000110. Now, bit 1 is set to a 1. This enables the interrupt. Bit 2, which is this one here, marks the last sample. And this operator here performs a bitwise OR operation, between the current value of this register and the 06 hexa. And then the result of this OR operation is stored back into this register. Basically, effectively, that sets a single sample. Now we come to this statement here. Basically, this is a bitwise operation between the contents of this register with 08. The purpose of this is to enable SS3, because earlier at the beginning of the function, we disable the sample sequencer 3. So here we enable it.
Demonstration. Okay, so here is a picture of my physical setup. Here's my LaunchPad board, and it's connected to a mini breadboard with a trimmer pot. Okay, so we are back into the Kyle Microvision IDE, and I have uploaded the code here. So let me just very briefly show you the code. So this is the header file, and then here are the my declaration of the 4 functions that I'm going to use in this program. And here is the main function. All right. And here is the declaration of the add result variable, which I initialize it to 0. Then I invoke the 4 functions: enable clocks, initialize port E, initialize port F, initialize ADC 0. Then here is the while loop, and here are the statements within the while loop. We've been through the details earlier. So here are the definition of the functions: enable clocks, initialize port E, and initialize port F, and then finally the initialize ADC 0. Right, so that's the code. So if I go to project, if I just push this up a little bit, clear the window. All right, we'll go to project, and then build target. I got 0 errors, 0 warning. And before I download the code, let me show you my setup. All right, so this is my setup. Here's my board. Here is the trimmer port. All right. Now, if I go to download, it should download it to the microcontroller board. So if I do that, it's already downloaded. Let's check the, you see the red light's off. So this green light here indicates the power to the board. Okay, so I've downloaded the code to the board here. Right, so all I need to do is press the reset button. Okay, so reset. Now the LED, which is around here, the red LED, is off at the moment. So notice the trimmer pot is towards to the ground, this side here. Now what I'm going to do is I'm going to turn the trimmer pot this direction towards the towards the 3.3 volts, and I'm going to turn it to a position where the red LED just turns on. All right, so let me just do that now. Right, so the LED just turns on. So leave it there. So what we're going to do is I'm going to measure the output across the trimmer port. So let me just get my meter, and watch out for this reading here. All right, we should read about 1.65 volts. Alright, this is 50% of the 3.3 volts.
Okay, so that's it for this video. I hope you have found the contents useful, and I thank you for watching, and I'll see you in the next video. Bye!